All right, welcome to WASA Distance Education. This is MBF3C, grade 11 math for college preparation. I'm Pete, I'm your teacher. So we're just wrapping things up now on lesson 14 of unit 3. So we started that yesterday. We did a few questions. And what I'm going to do today is continue doing some trigonometry questions where we kind of draw all of our different tools into it. Now, if I'm going to try to show a couple questions that aren't in the text, just to kind of add a little bit to it. Now, just some housekeeping here. Tomorrow is going to be a pre-recorded presentation, so you won't be calling in tomorrow, but we're going to wrap up unit 3 tomorrow, and we'll actually do a little bit of the rest of this lesson 14 as well, trigonometry. Okay, so tomorrow we'll wrap up unit 3. Now Thursday's class will be live again. Really, we probably should go ahead into unit 4, but what I'm going to do on Thursday is do a fairly thorough review of Unit 3 as well, and just go back through the trigonometry. It's one of the more challenging topics. I think you'll find the last topic in MBF3C maybe a little easier. I don't know. We'll see. All right, so that's it. And then after this week, we have a 1-week break, and you come back into week 7 of 9. So that's pretty quick. Now, yesterday we looked at the different examples, and we looked at the different sample questions. Okay, and the whole point here was we're going to look at the situation, put any information we have on our diagram, make sure we note any assumptions that we've made, and then we go and we'll sort of tackle a question. So we're going through that 4-step problem-solving model, and you know, if you sort of go through it consciously each time, it becomes a habit. Okay, and it becomes a habit for solving any kind of problem, math problems in particular, but really the 4-step problem-solving model. I mean, the first step is understand the problem, and that could be really anything, right? And then the step 2 is devising a plan of attack. You know, sounds very military, doesn't it? You know, devising a strategy for solving the problem. And again, that's something that we kind of need to have. Now, just because you have your strategy doesn't necessarily mean it's the most efficient one or the best one or even the correct one the first time you do it. That's where the practice comes in. That's where the experience comes in. Okay, so you know, and the first time you do a particular type of question, you might take the long road, but then you'll learn, and that's again part of the step 4 of the 4-step problem-solving model is that reflection. Did I do this well? Did I solve it as efficiently as I could? Did I use the right strategy? No? All right, I can use something different next time. And does my answer make sense? Okay, so that's what we're emphasizing here, that 4-step problem-solving model, or process as it's called in some places. You can actually look that up on the internet. There's lots and lots of places that talk about it. They sometimes make it pretty complicated with a diagram and stuff like that. The fact is it's 4 steps, and you know, they're pretty straightforward steps. So we saw the 2 examples, and we worked out one where we had to find the lengths, the angles just from 4 different lengths. And I showed you the way I do it, which is to just derive the formula that gives you the angle given the sides from the standard cosine law. Okay. Or you could just assume that you're going to have that available, which I think is probably a pretty safe bet. Okay, so that's what we did. And then we did one yesterday, which was kind of a cool thing. We were trying to find the area of a triangle, which is 1/2 base times height, or the way they give it in the book is base times height over 2. It's the same thing. And so we had to kind of pull out all the stops here. But once we took a look at the diagram and sort of educated the diagram, now this is in Unit 3 on page 35, right at the top, you'll notice that once I started putting the information on the diagram, and I identified what we had, which was one angle, that was it, right? I identified what we needed to know, which was the h, the height of that triangle. That's really, we had the base, 13.8 centimeters, but we didn't have the height. So, but once we got that, then it's pretty straightforward because we knew we had that 39 degrees. The height is actually the opposite, right? O is what I put, OPP, if you want to do it that way. And then we had the hypotenuse. So all we had to do was write down our SOHCAHTOA, which, pretty much, if you didn't know SOHCAHTOA and you went into a math class, a high school math class, chances are you would think everyone has the name SOHCAHTOA because that's what they write in the upper right-hand corner of their page, SOHCAHTOA. So you write that down and then you can refer to it. Okay, and you're not going to get, under this being nervous or whatever on the test. Now, for the MBF3C, we're going to give you the formulas. There's a sheet at the very end of the exam, and you got the formulas on that sheet, all the ones that you're going to need. Now, I caution you, I tried to avoid this for that sheet, just if you're thinking about it in the exam. I think there's a question on the other side of it, so to make sure you include that sheet back in your exam. So once you got your SOHCAHTOA, you can work out what you have and what you need. We needed the opposite. We have an angle and we have a hypotenuse. And so it was the sine ratio. We have the opposite and the hypotenuse and the sine of the angle that we have. Okay, and that's it. There's no real, the difficulty in doing these is really just the practice. You just need to get some practice solving problems like this. Now, yesterday where we left off was we were solving question 3, and it's a rather confusing situation. I think I started another page on it. It says calculate the height of the building in the diagram given. So this is the building right here, and I think what we have, I think what they're trying to show us is that there is a sort of a building here, and maybe it looks like that. Okay, and then this is the shadow of the building that we're measuring. Okay, so somebody's sighted up to the top of the building, and then they went out and they took a tape measure. They measured the shadow of the building. Okay, I think that's what they're trying to say. Anyway, okay. So the nice thing about that is that we can actually get this one. Okay, this is the opposite as far as the this angle is concerned, but we need either a hypotenuse, HYP, we need a hypotenuse or an adjacent in order to be able to find the opposite, right? But the nice thing is that this shadow triangle that we have here, okay, it gives us exactly what we're looking for, I think, because we have an angle here. Not really, and a distance. Yeah, I think we're going to be able to do that. Now, the reason why this is a 90-degree angle right here, so if we were looking at a top-down view of the building, I think what we'd be looking at is this shadow. The shadow looks like that. That's 45 degrees. That's 90 degrees, and that's 75. So this is the top. Okay, this is the top view of the building looking down. Right, so the sun is kind of over here. Okay, really is a little bit complicated to just sort of visualize it. A photo would have been a lot better, I think, for that picture question. Anyway, we get that though in math. Sometimes we get questions that are really kind of hard to understand, and that's where we spend more time on that first step of the problem-solving process. And then, once we understand it, everything's pretty trivial. So what we need is this thing here. This is the diagram that I did yesterday. And what we need is this x, because this x is this distance along the base of the triangle. And I don't know why I wrote b. I want h for height. And and this is a hypotenuse, and this is the opposite as far as the 61 degrees goes. So okay, so there's two triangles in. Let's I'm just going to draw this other triangle. Okay, this is the H, this is the building. This is the height of the building that we want. That's 61 degrees. And this X is the same X as we have down with this other triangle. So once we have X, then what is that going to be? It's going to be the tan of 61 degrees is, let's see, tan SOHCAHTOA, T-O-A, is opposite, which is H over adjacent. There you go. Okay. So once we have an A in this case, that's the adjacent. So we're going to change that into X. Whoa. Love this. All right. Sorry. Get another. Whoa. I don't know what I just did. Anyway, it's H over X. That's what we're looking for. So we need to know H. We can figure out X by attacking this other triangle. Okay. Again, I use the military analogy for geometry. I don't know. It's you read that a lot in the old textbooks. I guess maybe they were written a long time ago. They talk about attacking a problem. So let's take a look at this other triangle. Now this is the building shadow, and I've straightened it out so we know it's a right angle, because they tell us it's a right angle even though it doesn't look like it. We have a 45-degree angle there, and we have one side being 75, and we want to find X. So what do we have? What do we need to have? Well, this is the hypotenuse. We got to watch that we don't inadvertently try to put the hypotenuse as one of the sides. So as far as that angle is concerned, the 45-degree angle, X is the opposite and the 75 is the adjacent. So wow, we're still on that tangent ratio. So the tan of 45 degrees equals opposite, which is our X, and adjacent, which is 75 meters. Okay, so now you see that this problem is starting to fall like dominoes, right? We're gonna solve for X here, then we're gonna take our X and plug it into that other equation we made, right? Now, a common thing if you've got more than one equation is to number them. 1, 2, no problem there. Okay. That's just a common thing in math, and you'll see that if you take some college math, they will do that quite a bit. Some mathematicians use letters, A, B, C. It's really, it's up to them. I use numbers and letters. So we got 75 times a tan, 45 degrees equals X. Okay. Now, we know that X is a distance, and we know it's going to be in meters because that's what we started with. So let's take the tan of 45, which happens to be 1, times 75, which is 75 meters. There we go, 75 meters. Now, if I was writing this up, now my structure's not that great here as far as how I would structure this this question, but anyway, so I would write something like from 1, X equals, what did we get? 75 meters. 75 meters. Now, you see, I wrote that because that way, let's say I'm working on I'm working on this problem and I'm 10 pages in, and then somebody comes along, right? Like my friend who used to study with, and will point at something I did on the second page and say, no, that's a mistake. Right? And yeah, that happened a lot. So then you look at it, you don't crumple up your paper, you just go and you change it, you fix it. But then every place you use that number, you have to fix it. That's where writing your numbers in, right? So if I had a problem in equation 1, then I'd fix it, and then whenever I have something that came from equation 1, I can go back through my work and fix it. Okay, so from 1 we know that X equals 75, so now we're going to just keep going here. So a tan is 61 degrees equals H over 75, and then 75 times the tan is 61 degrees equals H, and H is the height of the building. Okay, and I think we can pretty safely just kind of, oops. Okay, tan 61 and then times 75 equals, okay, so 135.3 meters equals H. So H is approximately equal to 135 meters. Can't really round it much. Okay, so the building is 135 meters approximately, or whatever you want to write there. Okay. Now let's take a look at the scenario. 175 is pretty tall building, but it seems about right. I mean, it doesn't strike me as something terrible, right? What if we got 13.5 meters? That would be problematic because that doesn't seem like that would be correct for a building that casts a 75-meter shadow, right? And if it was 1,300 meters, 1.3 kilometers, again, you know, you're going to say, I don't know too many buildings that are 1.3 kilometers high, right? So that's where you, the fourth step of the problem solving process comes in, right? You're going to reflect. So it'll help us pick really big, you know, pick out really big mistakes, really, but it won't help us if we just made a, you know, we reversed a couple digits. It's not going to help us, right? So, you know, if it was 153 and I wrote 135, that's not really going to help us there, but it's fine, right? We can still do that reflection because then it also says, was this the right process? Seems like it worked pretty well, right? Maybe if I was doing this again, I wouldn't write the second equation first. I'd just write the first equation, solve it, and then write the second equation. Sometimes, or maybe I'd write them side by side because that's a good way to lay them out as well. You'd write 1 and 2, 1 on the left column, 2 in the right column, and then solve the right column and then transfer the answer up to the top of the left column. I think I got those backwards. Okay, so one way to organize these would be to say 1, and then you write it out, and then 2, you write it out, and then I'm just going to extend this page here. And then what you do is you'd solve this one, and then you got some answer, and then you'd bring that up to the second column and just start solving. That's a common way of doing these. But if you do a lot of them that are similar, then you get sort of experience in how to lay them out nicely. But in this course we don't do that many, so you know it's understandable that your organization might be just a little bit not as efficient. Still, it's good to think about it. Now let's take a look at the answers. Unit 3 support question. This was what was this one anyway? Um, this was question 3. Support question 3. Lesson 14. Support question 335.3 meters. So yeah, so they didn't round to the nearest whole unit. So I think that's fine, perfectly fine. All right, so so the next question, now we're on page 35 of unit 3, and I'll just back up here and we can find it in this. So now there's no diagram to go with this one, so that's where we want to kind of have to read the question, really go through that first step of the 4-step problem solving model really well. Okay, so it says 2 chains support a weight at the same point. The chains are attached to the ceiling and are 6 meters and 5 meters in length. The angle between the chains is 105 degrees. How far apart are the chains at the ceiling? Wow. That's not really something that I would normally be thinking about, what a chain looks like hanging from a ceiling. I'm wondering if it maybe like Christmas ornaments or something, you know, like a garland, and then they could put a ball to hang a decoration, like a glass ball on it. I don't know. Or maybe this is something in a factory, I guess, you know, something they use as part of their hoisting, you know, or something like that. Okay, so in order to do this, I'm going to have a diagram now. When you're doing these, I suggest you use a separate sheet of paper. You don't have to rewrite the question if you don't want to. You know, I don't really consider it all that necessary, but certainly doing a diagram when you go to work out the question. So this is going to be page 35, And this is support question 4. Okay, and that's unit 3. Okay, unit 3. There we are. Now, so two chains support are weighted at the same point. The chains are attached to the ceiling. Okay, and there's 6. Okay, the angle between the chains. So basically, they're describing a triangle. I'll do this in blue here. So there's the ceiling. Okay, this is the ceiling. Okay, and so then this is one of the chains here. And then that's the other chain right there. I'm going to clean this up a little bit. All right. And, so this is, okay, so one of the chains is 6 meters long. Okay, so there's a chain. That's a chain. And then the other one is 5.5 meters, 5.5 meters. And so basically what they're saying is that these chains are holding on to a weight. Okay, and then they're attached somehow to the ceiling. And then we want to know what this distance is. Let's call that x. We don't know what that distance is. Okay. Now, what other piece of information do we have? The angle between the chains is 105 degrees. 105 degrees. Okay, we're good. We're good. 105 degrees. I think we're gonna be all right there. Pretty lousy looking degree symbol. Let's see if I can do that again. Okay, and again, it's it's just a habit. It's not for this particular problem because I'll be done this problem. But if I do a piece of mathematics that is part of my work, right, as part of a report or something, I want my writing to be readable even a month later, 6 months later, or by someone else, right? So that's why, if I see some sloppiness, I want to go back and fix it. Just a habit. So, all right, so that's the geometry, that's the situation. Obviously, those are straight lines. We're assuming they're straight lines. And we need to figure out how to solve for x. So the first question then is, so I think we've understood the problem. So that would be step 1, right? Step 1 of the 4-step problem solving process. Step 1, understand the problem. That is everything we know about the problem. We have identified all the information we have. We've identified the piece of information we need, the one piece. Now, step 2 then is to work out our strategy. And part of that strategy could be there might be more information we need. Okay, it is possible. So, let's see. We don't really, we can't use any of the trig identities, the SOHCAHTOA. We can't use those because there's no right angle here. Now, one of the tricks that we sometimes do in geometry is we'll drop a perpendicular down, and then we form 2 right angles. The problem with that here is that it doesn't help us. If we knew the distance from the ceiling to the top of the weight, that would help us, because then we'd have the distance of that green line. Or if we knew maybe where that perpendicular would hit, it's not necessarily going to be it's not going to be exactly in the middle of the distance, right? You can't assume that. It might look good, but that's not the case because the 2 chains are different lengths. So it's definitely not going to be straight in the middle. So I'm going to just take that, hopefully, take that line away. But that is one of the ways that sometimes we attack these problems if we have a bit more information, right? Maybe we know the height of it or something. So we can't use that. So what's our next thing? Well, can we use the law of sines? Okay. Would the law of sines actually help us? Well, it would help us if we had one of these angles. It would help us. The problem is that we have one angle, and it's across from an unknown, right? So if I were to say the sine of, actually, let's put x over the sine of 105, that's great, right? But here's the problem. The problem is that if we look at the other 2 sides that we have 6 meters over here, Okay, and we have 5.5 meters over here, but we don't have any angles, right? If we had one other angle, then we could do this, right? But we don't have those angles, so the law of sines isn't gonna help us. Okay, so that's nice try, but yeah, well, we tried anyway. But you see, that's the sort of process you're going to go through when you're doing that second step. What do I have? What do I need to know? What, how can I kind of get this sorted out? Okay. So I think we're down to the kryptonite, aren't we? Right? The law of cosines is got to come to the rescue here, because we can't use our trig identities. Can't use the law of sines. Got to use the law of cosines. So how are we going to structure the law of cosines to help us here? We need x. So if we use the format of the law of cosines, we'll say that x squared. Now remember, I don't try to memorize the different formats of it. I just know the pattern. The pattern is that the side we want is equal to the sum of the squares of the two sides that we don't have, or sorry, the two other sides. Sorry, 5.5 squared minus. Okay, and now things are going to get a little bit. Let's see if I can move all this. I sort of ran out of room here, so the miracle of that's actually pretty cool. I'm going to extend the page anyway and then scroll back. Sorry about all that. Okay, so minus 2 times, and this is the 6.0 and the 5.5 times the cos of the angle that we have, which is opposite the x squared, which is 105 degrees. 5 degrees. Wow, just barely fit all that in there, but that's what we got. Okay, now I'm just going to go back and fix up that last little bit here. Just um, cos 105 degrees. That's better. So if we look at this, this is this is kryptonite. It's going to solve our problem for us, because everything we need on the right hand side is there. That's all going to turn into a single number. And then on the left hand side, that's the very thing we need. We've got to take the square root of both sides at some point, but that's everything we need. Okay. So sometimes you got to break out the big guns here, I guess. To boy, that's a lot of military stuff in math, isn't there? Okay. Um, all right. Now let's see if we can solve this. So we got x squared equals. Now I'm just going to go through it. I'll do it in a couple of steps. Um, you know, we can do it in a couple of steps. Plus 5.5 squared. Just make sure we get everything. So it's 66.25 minus, and so it's 2 times 6 times 5.5, and then it's 66 times cos 105 degrees. Okay, this is looking better. So x squared equals 66.25 minus, so what is cos 105 degrees? Cos 105 degrees, it's a negative number, times 66 equals, okay, so it's negative 17. So we got to go negative 17.0820569. Why not? Just put them all down. It's in the calculator. Now, remember what I told you way back in Unit 1 about how we resolve this situation right here, where I have, remember, that's a negative 1 times what's inside, and the effect of it is that it flips the flips the sign of everything in the brackets. There just happens to just be one thing in there, right? Okay, so x squared. So 6.25, and so we get 83.3321. I'll just truncate it or round it off to 4 decimal places. Now, remember that we need the square root of both sides. this is kind of the one way to show that. There's others. So now I'm going to take the square root. Now, the number of digits I have in my calculator quite a bit more than what I've shown there. All right, 9.1286. And now we'll take a look at what they gave us. They gave us everything was to one decimal place. So let's just round it off to one decimal place. 9.1, and our units should be meters, right? 9.1 meters. All right, let's go back up here and take a look. So according to our calculations, this is 9.1 meters. Does this make sense? It looks about right, doesn't it? If it was closer to 6 meters, then we would expect these angles to be closer to 60 degrees because it would be closer to an equilateral triangle where all the angles are 60 degrees. So 9.1 meters makes sense, okay, to me anyway. Let's take a look though at what they have to say in the solutions. Oops. Okay, not quite. Okay, so we'll look at the back of Unit 3 here. And so this is lesson 14, support question 4. Okay, lesson 14. That's right. Okay, 9.1 meters. Wow, look at that. Okay, and they actually show you how they did it. Oh, they even show you a picture of it. Oh, well, that's interesting. So it's kind of nice, right? It's nice to be able to see that. Now, if you're working on math problems, and let's say that you go to college and you're working on your math, what I suggest you, it's nice to be able to look up the answer, isn't it? What I suggest you do if you don't have the answers, because a lot of times you won't, is you get yourself some buddies, some other students who can who are also working on the same course, right? People who are serious about it, who wanna do well in it. And what you do is you work together, right? Form a little study group, homework group, whatever, and you can each do the problems and then compare your answers. And that is, it might even be better than just looking at the answers in the back of the book. Okay. And the reason it's better than looking at the answers in the back of the book is because you know what, you all had the same instruction, right? You all had the same professor, so you're going to know kind of what that professor expects. And so if you drew a diagram and then you looked at your friend's diagram and they were different, then you could talk about it. And you say, well, why did you do it that way? If your answers are different, you could work through it together and seeing where, you know, things went off the rails, either you or them, that can really, it can really help you. Okay, so that's a little tip. Works in high school, works in college math, works in university really well too. Now, do we do it? It's meters, right? We want to make sure that we're measuring a distance and not an area. So that's pretty good. All right, well, so those were the support questions. Let's take a look at the key questions and see what we're gonna do with those. Okay, now we're not gonna solve the key questions, but oops. Okay, I gotta back up a little bit here. The bottom of page 35. Okay, so now here's an example. At the beginning of the trigonometry section, I told you that we normally label triangles, ABC or DEF or something like that. And we skip I's whenever possible and O's just. Now here's someone that's decided that they're going to name the triangle um, people names, and then they're going to use the first letter of the name as the angles, and that's perfectly fine, right? That's how mathematicians are able to do stuff like that, right? So it says Noah and Brianna, so N and B, want to calculate the distance between their houses, which are on opposite sides of a water park. Okay, so there's Noah right there, and there's Brianna. So already, I might have drawn it. If I didn't have a diagram, I might have drawn it like this. But it doesn't really make any difference. We're still going to have the we're still going to have the same answer at the end, right? So Noah and Brianna want to calculate the distance between their houses, which are opposite sides of a water park. Okay, so I guess the water park is Okay, so this must be the water park in here. Okay. Okay, right, yeah, makes sense. That's pretty good. Yeah. If you go to Florida, a lot of the houses have that. They call it a what do they call it? A lake view or something? Well, it's an artificial water. It's a pond, basically, an artificial thing. Okay. So they mark a point A, 150 meters along the edge of the water park from Brianna's house. So there's point A. Okay. Um, and then they measured NBA, which is a very complicated way of just saying angle B. Um, okay, it's fine. But a lot of times they'll do that in math. They don't want you to, make a like accidentally get the wrong angle. Okay, so for very complicated diagrams, that's a perfectly fine way to do it. But anyway, angle B is 80 degrees, and then A, angle A is 75 degrees. Okay, and we have that right there. So there's angle A, there's angle B. We've got it. Okay. Determine the distance between our houses. So where's our X going to be? Well, it's Brianna's house. That's Noah's house. So there's our X right there. So do we have everything we need? Okay. So the question we're going to ask ourselves, can we use SOHCAHTOA? Okay, can we use SOHCAHTOA? Can we use the law of sines? And if not, then we're going to have to, how do we use the law of cosines? Okay. So you'll have to look at the situation here. It doesn't look like it's a right angle, but you want to read the question and make sure that that's indeed the case. It's not a right angle. Okay. All right, well, because it's a key question, I guess I probably shouldn't try to solve it. But let's take a look at a second one. Oh. Okay, here we are. So the second one, now this is an interesting problem. This is so one of those observation tower type questions, and I actually have one here that we might be able to get to. So it says, from an observation tower that overlooks a small lake, okay, the angles of depression of point A on one side of the lake and point B on the opposite side of the lake are 7 degrees and 13 degrees respectively, right, one after the other. The points on the tower are in the same vertical plane. Mm-hmm. And the distance from A to B is 1 kilometer. Okay. Determine the height of the tower. Okay. So this is the same vertical plane. Okay. So I guess they're talking, I'm not really sure what that actually means. But anyway, I think what they're trying to say is we can assume it's a right angle. I think so. So we know that the points A and B are 1 kilometer. So what happens is, and this is kind of a common surveying thing, okay, we know that point A and point B is 1 kilometer, right? And so somebody put a coin on the ground or something like that, and then somebody climbed to the top of this tower, okay, and then they looked down and they measured this angle here and they measured that angle there by looking at the coin or whatever the marker was. And from a horizontal line, the angle of depression, 7 degrees and 13 degrees. Okay. So that's what we have. It's a pretty common thing. They don't tell us how tall a tower is. So we don't have a whole lot of information, but I think we have enough. Okay. So how are we going to solve this? Okay. Well, one of the things that we can do to solve it, we might have to introduce something else. Now, you could go ahead and solve this. One of the things you would probably do, you could get the height of the tower by, you probably, no, because see, the 1 kilometer, it's from A to B, but it does not include, you can't assume that it's in the middle, right? So don't make that assumption that it's 500 meters from A to the tower and 500 meters from B to the tower. That would be a faulty assumption, because we know that this line here and that line here are different lengths because the angles of depression are different. Okay, so if the only way that the tower could be right between A and B is if the angles of depression were the same, and then you could make the case. Okay, but we can bring in a little bit of, I mean, there's lots of ways to attack this. There's a lot of ways to solve this. But one of the things that you know, maybe if it's been a while since you've done your, um, you've done your geometry, trigonometry, stuff like that, we know that this angle is 7 degrees, and because of that, we know that that angle is also 7 degrees. Okay, it has to do with um, interior angles of a line that crosses two perpendicular lines. Okay, and the two perpendicular lines are the dashed line and then the line between A and B, right? So if we kind of think of this as going out here, okay, there's a basic geometry law that tells us this angle and this angle are the same, and by that same token, this angle and that angle are the same. Okay, so you know that that angle is 13 degrees. Okay, now you could work that out, but that gives you a real help there because now we could get that angle, okay, because we know that that's a right angle and that's a right angle. Okay, so we have this angle, that angle. You could work out this angle. You could work out this other angle here. And then knowing an angle and a distance, I think that that might help us. Yeah, and another angle. And then all we need is a distance, like, yeah, any of these distance. Oh, we do need the height of the tower. Oh, okay. We need the height of the tower, right? H. That's what we need. So, so there you go. That, for me anyway, is, you know, solving the problem, coming up with an understanding of it. So probably to me the best thing to do now would be maybe to go off and kind of redraw this. We know that that's 7 degrees. That's H. We don't know. Oh, okay, we don't know what that. Yeah, you know, we're going to have one of these. And those are the hypotenuses of the smaller triangles. But these are also sides of the bigger triangle. And we have enough information to solve. I'm going to draw it in green. We have enough information for the bigger triangle to solve either that one or this other one I'm going to draw in red, right? Because we have a side, we can work out that angle, and matter of fact, we have all three angles, so we're golden there, right? Um, yeah, yeah, because this green here, the angle opposite the green is that one right there, the 13 degrees, and yeah, so I think we could solve that. So this is a multi-step problem, and hopefully, you know, sort of giving you a little hint um, about how to proceed. You're going to have to work out one of the sides of the bigger triangle, um, you know, one of the two remaining sides, and then you're going to apply. Then you use the trig identities in one of the smaller triangles to find the height. Okay, and that's yeah, that's it. Okay, the common mistake here, and I think the reason why I really want to talk about it is that we cannot assume just because A and B is 1 kilometer, we can't assume that the tower is between them. In fact, it won't be. Um, I would encourage you that once you found H, to go ahead and work out this value right here, the length of that, and then that one right there, and you'll see, or actually just one of them, and you'll find that it's not 500 meters. It'll be a little more or a little less than 500 meters. Okay, so there we are. Okay, well, let's take a look at question 3. We're going to leave question 4 for tomorrow. Remember that tomorrow's class is pre-recorded. And I happen to know that that's where I started from. Oh, I'm sort of giving away some of the, hey, you can look at it. So yeah, so we started with question 4 for tomorrow's broadcast, and then we went in and we did lesson 15. It's not a very long unit, so not a very long lesson. Well, let's take a look at question 3. This is key question 3, so you'll be handing these in. Children's play area is triangular. They all are, aren't they? The size of the play area measure 100 meters. Wow, that's a big play area. 100 meters, 250 meters, and 275 meters. Not a play area. That's like a play field. 100 meters, 250, respectively. Calculate the area of the play area. Ooh, wow, this this could be a very cool question. Now, if you're wondering how to go about that, we actually had one that was similar in the support questions. I think no, the examples. I think the second example. Um, no, first example. Maybe. Anyway, it was one of them. It was okay. Oh, maybe I'm getting. Oh yeah, a support question too. It was pretty much like that. Um, yeah. Okay. So let's take a look. We'll start a new page here, and this is how you kind of have to do something like this. There's no real getting around it. So I'm just going to draw the triangle. Now, what I'm going to do, just because I've done a few of these before. By the way, this is key question number 14, part 3, and that's on page 36. Okay, so now I've done a few of these, so I'm going to put the longest side on the bottom, 275 meters. Okay, and so then it's going to be 100 meters, 250 meters. Okay, and there we go, 275. And we want to know the area of this thing. Okay, well, the area equals 1/2 base times height. Okay, now this would be our base right there, and the height in a triangle is measured by dropping at, whoops, okay, let's just, is by dropping a perpendicular, okay, the reason I'm off a little bit here is my smartboard is not exactly calibrated. There we go. Okay, so what you do is you take a perpendicular from the baseline and go straight up into the angle on the top. Now, the only thing you can assume there is that this is a right angle. You can't assume anything about whether that bisects the angle. You can't make any assumption about that, nor can you make any assumption about how far this perpendicular is on the baseline. Okay, it's not in the middle. You can't assume that. That's all you have right there. Okay. So we already have then base, and what we need then is h, the height, which is going to be this value right here. So we need the height of that. Well, in order to get the height of that, what do we need? We have this. Okay, so that's the hypotenuse of a right angle if we look at the smaller triangle, right? And likewise, over here, the 250 is the hypotenuse of a right angle, which means that if we had this angle here, or, well, I guess, that's probably the one, or that angle there, then we would be able to solve for each, the small triangle. So how do we get this angle here? We call this, I don't know what we want to call this. Call this big X, something like that. How do we get big X? Well, I think hopefully you can see this, right? If we look at the big triangle, we have 3 sides, and we know how to deal with that to find an angle when we only have 3 sides. You might look through your notes, look through the examples, but that will kind of help you, right? Help you sort through that one. Okay, so hopefully that's to kind of get you going here. I'm not showing you the answers to the key questions, but I want to give you some strategies and some ideas. And this is because we're doing everything over the air. It's a little more complicated. Normally we'd be doing this in a classroom. I'd be walking around and helping you with this. So if you have any questions, this can be a little tricky. So if you do have any questions, don't hesitate to contact me. You have all my contact information. and you can always reach me on Facebook, which is, oops, let's try that again. PW space Wassa. Okay, if we're not friends already, just send me a friend request and then send me a message. Okay, and you can take a picture of any kind of work that you're doing and post it on Facebook in a private message. It won't go anywhere. Or you can text it to me, and you'll have to look at the study guide to get my cell phone number. You can text it to me. Picture of any work or any question you're working on, and I'll get back to you. So that's going to wrap it up for today. Tomorrow will be pre-recorded, and then we'll come back live on Thursday. All right. Take care.